people. Welcome to kind of our second to last thing. Well, this is a big boy, as you've seen by the packet. Waves and what we call simple harmonic motion. This covers a lot of material. This simple harmonic motion piece, yes. What are all those dots? This simple harmonic motion piece is not the most important part, but it's kind of definitional thing. And yeah, simple harmonic motion. By definition, that means that an object's position and acceleration are directly related. All right, and objects that demonstrate what we call simple harmonic motion, well, that motion or some, I don't know, that phenomenon, we'll say in general, can be represented as a sine wave. All right, depending on what you put on the axes. What kinds of systems demonstrate simple harmonic motion? Well, one of them is a mass on a spring. Okay, I'm going to touch base, or sorry, not touch base, but I'm going to come back to this slide on Monday when I see you next. So in 10 days from now, probably tomorrow for most of you. Get it? Because you just started finally doing this Sunday night. I recycled that joke. I think I used it over Christmas break or something. What are you going to do? So yeah, ask me about this simple harmonic motion thing and why it has to be a sine wave or cosine wave. Okay, but a mass on a spring is one system that demonstrates what we call simple harmonic or periodic motion. So here's mass on a spring, and like I said, lots of systems can be represented as a sine wave, depending on what you put on each axis of this graph. So we could put something here like, I don't know, position, right? Sure, we put position and time there, then yeah, the position oscillates, we say, about an equilibrium position, and over time, well, that, it goes above it and then comes back and goes below it and then comes back and above it, and so on and so forth. Right? A pendulum is also a classic demonstrator of simple harmonic motion. Here, we would do probably angle on one axis and time on the other. Okay? And a sound wave, right? Lots of times we draw sound waves like this, but sound waves are very different, right? Sound waves, there's an oscillation in what we call, well, in something like this, whatever this is going on. These are supposed to be particles of air, right? And what happens is particles of air go from being what we call compressed or packed together to what we call here rarefied, which means spread out. Sometimes you'll hear the phrase sometime in your life. You'll hear the phrase the rarefied air, in the rarefied air, which means it means up high, right? Up high, the air is not as dense, right? It's spread out, and up high, we talk about rarefied air, people existing in rarefied air because they're way high above everyone else. So anyways, so what can you plot there that says something's big and something's small and something's big again? Well, we could say particle density. That says density. Trust me. Over either position or time varies. Okay? Fair enough? So even though sound looks nothing like this, nothing in sound actually moves up and down, we can represent what actually happens in sound with a sine wave, as long as we're careful about what quantities we're really looking at. Okay? Okay, so onward. Yeah, main point. What do waves do? All waves do the same thing. There are lots of kinds of waves. Scream some out. Don't scream on. Just what kind of waves have you heard of? Ocean waves, of course. What else? What else? There are light. Light sometimes behaves like a wave. Of course, sound is a wave. There are waves on. There are seismic waves, right? Like earthquake waves, the P and the S waves. All those waves, they all do the same sort of general thing, and that is that they transfer or transmit energy. That's what waves do. All right, and they can do that without transmitting or transferring. Transmitting? Yeah, transferring, transmitting, same thing, or combined, without transmitting matter. All right, that's a neat thing about what waves can do. They can move energy around without moving stuff around. Okay? And waves, well, there are two main kinds of waves. They're what we call transverse waves, like this, where a part of the wave itself, as the wave, what we call propagates, or this wave, this peak here, what we call a peak, can be moving that way. But this part of the wave moves up and down. All right, so the particles do what we call oscillate or vibrate back and forth perpendicular to the direction of the wave's propagation. So here's V. And the particle moves up and down there. I mean, this particle, if we look at a particle right here, what's it about to do? This is confusing for people. People say, well, it's going to go this way. Again, the particle doesn't move this way. All right, the wave does. So what we have to say is, what's coming this way? Right? Well, this peak is coming that way, so this thing's actually on the way up right now. As that peak gets to it, it's going to end up here, and then as this not peak gets to it, it's going to come back down. So you have to look at what was coming before it, or what's about to get to it. Okay? And the other kind of wave is called a longitudinal wave, in which particles oscillate parallel, maybe no surprise there, to the direction the wave moves. So that's more like this thing, right? Where, this, what we call compression, or this peak, is traveling, the wave travels that way. But this one particle right here, what does it do? It goes back and forth like that. All right? We're going to do some sort of, classification of waves. Clearly is transverse or longitudinal. And the big one for transverse is light. When we treat light like a wave, and we won't always, but when we treat light like a wave in this unit, light is a big example of a transverse wave. All right? And over here, sound is the big example of a longitudinal wave. Okay? Okay, definition stuff. 3 points. Gotta know it. I made up a word, transmittering. Next, other distinction between waves. Well, waves can be either mechanical or non-mechanical. All right? And mechanical means a mechanical wave. Come on. Am I running out of battery? A mechanical wave has to have what we call a physical medium to travel through. There has to be some stuff. Okay. There has to be some stuff that the wave travels through. Like, for example, either, I can't express to you how frustrating that is. Can you come back? Yeah, great. Like, not light, stupid, liquid, or solid, or gas. Some stuff. Mechanical waves have to travel through stuff. We'll get back to that. Non-mechanical waves do not require a physical medium. That means they can travel through nothing. Or a vacuum. Are there two C's in vacuum? I have no idea. Tell me, don't look them up. Tell me more words with two U's in them. The two U's. The big example, oh yeah, can travel through a vacuum. Exactly. So, what do you know? Vacuum. Of light or sound, kind of those are our two big ones. Which one's mechanical, which one's non-mechanical? Well, only one of those can travel through a vacuum, like the vacuum of space. Well, of course, light can travel through the vacuum of space. Sound cannot. Can sound travel through liquids, solids, and gases? Absolutely. Wait, did I say sound? Can light travel through liquids, solids, and gases? Sure it can. But it can also travel through nothingness. Therefore, it's a non-mechanical wave. There is no sound in space. Therefore, sound is a mechanical wave. Now, I know we said in the last slide that sound is a longitudinal wave, right? Sound's also a mechanical wave. That doesn't mean that longitudinal waves are mechanical waves. It doesn't mean that mechanical waves are longitudinal waves. Right? These are just different ways of classifying waves. Okay? Parts of a wave. You've heard of lots of these, of course. Yeah, sure. I'm just seeing what's going to... Yeah, okay. Come on, you dummy. Whoops. What? Bear with with me, people. Mild disaster. Okay, so parts of a wave, we call this, we call this a peak or a crest. We call this the thing that pigs eat out of, a trough. What else? What else? Oh yeah, we call this amplitude from the equilibrium to a peak, or from equilibrium to a trough, not the whole darn thing. I think the whole thing from peak to trough is called the displacement, but we don't usually talk about that. Other things. Now, this can get a little tricky. Depending on what's on this axis, let's say that this axis measures time. Well, this amount of time for a full cycle is called period. We've heard of that in our circular motion stuff. The time to go through one full cycle. That's called period. Now, sometimes there might not be, I'll say, or there might be, this might be a plot of something versus position. And if this is a distance, we call it lambda. Lambda. And that means wavelength, measured in meters, like this t is measured in seconds. So, really depends on what's on your x-axis. If it's an amount of time, then we can see that amount of time for a full cycle, we call it a period. If it's an amount of distance, the distance between two successive, or two, whatever you want to call them, points on a wave is called the wavelength. Anything else here? No. I think so. This is going to do, yep, parts of a wave, very good. Wave speed v. You will notice there are things on this graph that we could use to find speed. All right, we could use, oh yeah, look, meters and seconds to find speed, because speed's in meters per second. So if we did lambda divided by t, that would give us speed. But we usually don't do it that way. We know that, remember this, 1 over period, well, oh yeah, we called that frequency. Frequency. So what you will see, excuse me, what you will see is this. Wave speed is f times lambda. Frequency times wavelength. Okay? One more thing pops up. Where is it? At the bottom? Move. Love a beat. Yeah, wave speed. Now this says, well, gee, if I mean, what is the deal? You're gonna hear me yell. It's Friday. I shouldn't be mad. Shouldn't be angry. Whatever. This said wave speed depends on. It looks like wave speed depends on frequency and wavelength, right? Oh, if frequency is bigger, then velocity is bigger. If wavelength is bigger, not true. Not true. Not true. Wave speed depends only on the medium through which the wave travels. All right, light moves at a certain speed in air, and that speed is constant. That means that these two things are inversely related. Larger frequencies have smaller wavelengths. Big frequencies have small wavelengths. Wave speed depends only on the stuff the wave is moving through. Okay? Okay. Oh, good. 15th time. Super. Yeah, other ways to depict waves. As a wave front. You will see, we won't always draw waves like this. It becomes a little bit cumbersome. Sometimes we'll draw waves like this, where we're kind of doing top view almost of this. Whoops. A line there, a wave front, right? These are all wave fronts. Is supposed to represent a peak. All right. The nice thing is, if we look at these things like this, like wave fronts, we can say, oh yeah, look, we can tell the wavelength, right? Distance from peak to peak. Even simpler, sometimes we'll just say, oh, there's a wave. Now look at that, there's my wavefronts. It's amazing how close I was. We'll just say, yeah, waves going that way. We don't really care so much about characteristics of it. We just care about where the light goes. We'll use that a lot for light. We'll do a whole section, what we call ray diagramming. Okay? Here's a little something example. Please take a run through that. You. Text. Yeah. Fill in the blanks. Also you. Yes. Now, what do different sounds sound like? No. What do different sounds sound like? Well, I got to show you that, which means I got to pause this real quick. Yeah. So I just hooked up this the Lab Pro thing. We used to connect motion detectors to this. Remember? And this is the thing we used at the pep rally to measure how loud people were in arbitrary units of sound pressure, whatever that means. So what we're going to do is look at a couple different sounds. We're trying to talk here about what different sounds look like, or what different waves sound like, if we're focusing on sound for a few minutes, right? So what I'll show you is, let's see, if we record a little bit, and I know what you want to see. You want to see this thing like scribbling up and down like this while I'm talking. Blah, blah, blah. It doesn't do that. It just collects data for a very, very short amount of time. Look, 3/100ths of a second. All right, so I'm just going to do, you're going to hear my beautiful voice. Ready? La. Oh, wait, I can't press that button for some reason. I got to put the pen down. Ready? La. Damn it. La. Wow. So I don't know what that's supposed to look like, but whistling works better. Let's try that. Right? Aha! So there's a sound. All right? And we see, from here to here is a wavelength. Okay? And if we want to make this look different, well, I'm going to try this. Watch. Oops, got to put this down. Listen to the difference in the sound. Aha. So hopefully you can tell that, I don't know how well you can hear that, but I was whistling more softly, like the songbird that I am. I've been called the songbird of my generation. What's that from? And you see that what changes, right? What changes when a sound is softer? Well, hopefully you can tell that the amplitude of that wave is smaller. Yeah, there's a bigger amplitude, louder sound. Okay, so the other thing I'll show you is, let's see, now I'll drop that down a little. Whoops. Aha. So now we had a lower pitch, and where here was our wavelength before, now our wavelength looks like that. You can actually tell. For the musical types out there, perhaps, you know what change in pitch that was? It was an octave, unless my pitch is really bad. And maybe you can also tell that that wavelength doubled. I don't know if you can tell that or not, but that's what happens. So my performance is over, I think. So what we should be able to see here now is that, let's take this sound. Compared to that sound, what does this one sound like? Well, it would be...
Please excuse this interruption for one afternoon announcement. Any students in Mrs. Coff's 10th grade honors AP class, please come quickly to B as in boy 116 to get your permission slip for the New York City field trip, which is going to take place on March 13th. Thank you. Everyone have a wonderful vacation.
Thank you, Mrs. Porter. This sound would be, anyone? Yes, louder, right? But it would have the same, Notice they're the same number of cycles in, 15 whatevers, 15 seconds, I don't know. So it would have the same pitch, same frequency, same pitch, right? Volume for sound is determined by amplitude. If this were light, what would be different? Let's call that U. Don't look it up. what do you call it? Don't go look it up. Think and see what you come up with. What do you think would look different, about this light compared to that? Okay? Now, there's probably a nice little graphic here, or animation perhaps. Oh yeah, get it. Look at this. This is so cool. So over here on the left edge, this gray thing is it's like the cone of a speaker oscillating back and forth. And what that cone does is it pushes air particles together, and then pulls back and spreads them out. Right? And you can see these wave fronts, right? Here's one right here, moving along slow, right? Makes it look like the particles of air are just traveling down that tube. But look at our little red guy here. All it does is oscillate back and forth. Cool as heck, right? I sure think so. Okay, so remember, for these longitudinal waves like sound, it's just that, this is our peak. And our peak, now it's over here. And our peak is now over here. Right? So our peaks are traveling, but the actual particles themselves are just going back and forth. Okay? Way cool graphic, says me. Now. Poop. Right, go. Yes, now compared to this same sound that we compared to before, how do you think this sound would sound? How do you think this wave would sound? Well, it would have, what's the same about it? What's the same? What's the same is the volume. Yes, of course that would happen. The volume is the same. All right, but it would have, well, notice, the frequency is higher, so it would have a higher pitch. We saw that hopefully during my beautiful demonstration of whistling. So pitch for sound determined by frequency. Notice we're talking a little more now about frequency than we are about wavelength. We can look at wavelength and see it here, right? This could tell us what the wavelength is. Again, if this is something measured in meters, right? But if we look at, lots of waves per unit time or per unit space, that means high frequency. Okay? And you try that. Okay? What's next? I think next is, what's up, brother? Oh, yes, waves. Things that waves do. We'll hang on to that as we're getting around the perfect length of a video. But I will just show you. I can't resist. Here's something that waves do. Listen. Listen. You hear that? You hear that change in pitch? That change in pitch. Right? That's something that waves do. We got to talk about that. That's we'll pick that up on Monday. All right? Have a great break, or I hope you had a great break. Peace out.